For investigation 8A, which is called Forces of Wind. I think a more appropriate title for this investigation would be Forces that Act on the Wind, and that's exactly what we're going to be doing here today. We're going to be talking about the forces that act on the air that ultimately lead to the winds that we observe primarily at the surface, but I'm also going to mention upper air winds here just briefly as well, because the forces that we describe here today also apply for winds above our heads as well. So let's get started with the PowerPoint and start our slideshow. So forces of wind. Now what I'm going to do to begin with is I'm going to start with the three basic forces that act on air at the Earth's surface. The first one is the pressure gradient force, the second one is the Coriolis force, and the third one is friction. Each one of these forces by themselves will cause movement of the air. The pressure gradient force we'll see is the only force that can actually act on air that is not in motion. So the Coriolis, or I should say the pressure gradient force, is always the force that kicks off the wind. And then once the air is moving at the surface, both the Coriolis force and friction act upon that moving air to give us the winds that we observe in the real world. When we're talking about upper level winds, basically all we do is we eliminate friction. So we basically talk about the pressure gradient force and the Coriolis force. So to begin with, we'll start with the first figure in the investigation. This is a hypothetical surface map of isobars, parallel east to west isobars. 1,008 in the south, going down to 1,000 in the north. So basically, we have pressure decreasing from south to north in this figure. And we have a point A here in the middle, right on the 1,004 millibar isobar. What I'm going to do in the next slide is I'm going to take that A away, and I'm going to put in the pressure gradient force. The pressure gradient force is a force that acts on air where pressure changes over distance. And the pressure gradient force is always directed from high to low pressure, and it is perpendicular to the isobars. So when I draw the pressure gradient force on this particular schematic at point A, this is what it's going to look like. And we're going to basically use arrows to depict our forces. And the arrow itself has two components. The first one is its direction. So the direction of the arrow in terms of where it's pointing basically is pointing in the direction in which the force is acting. And then the length of the arrow will be proportional to the magnitude of that force. So the bigger or the longer the arrow is, the larger the force is. So in this particular example, the pressure gradient force is directed from high to low pressure, perpendicular to the isobars. And so that's what we see here. Now the second force that acts on the wind is the Coriolis force. Now remember, I already said that the pressure gradient force is the only force that can act on wind, or I should say air that is not in motion. So the pressure gradient force always kicks things off. That gets the air moving. Once we actually have a wind that is initiated by the pressure gradient force, then we can start to look at the Coriolis force, and then after the Coriolis force, we'll talk about friction as well. So to understand the Coriolis force, and how it works, how we get it, you have to take a look at the Earth and remember that the Earth rotates about its axis once every 24 hours. Now, the direction of the rotation, if you're just looking at the Earth from outer space, is basically from west to east. And so this blue arrow indicates the direction of the rotation of the Earth about its axis. Now, as the Earth is rotating about its axis, what you should keep in mind is that it doesn't matter where you are on the planet, whether you're here roughly at the equator or whether you're moving at the poles, towards the poles, no matter where you stand on the Earth's surface, if you stay planted at that location for a 24-hour period, you're going to go around one complete circle of the planet at your latitude. So if you think about it, the circumference of a latitude band at the equator is the largest it's going to be on the planet. And then as you move towards the North Pole, for example, the circle gets smaller and smaller and smaller until when you're standing at the North Pole, the actual direction of rotation is still going to be west to east, but the actual, what we call radial velocity, is going to be zero. So in better words, instead of moving from west to east, you're just going to be standing at a point and rotating very, very slowly once every 24 hours. So we have these radial velocities, and radial velocity varies from a maximum at the equator to zero at the North Pole, and it's latitude dependent, obviously. So before I actually go and define the Coriolis force, what I want you to do is imagine that you're somewhere on this blue arrow. And so you're basically at the equator. And imagine that you're golfing and you have the ability, you have the power to actually hit a golf ball all the way to the North Pole. And so my question to you, and I'm going to give you the answer as well, is if you hit that golf ball as hard as you possibly could towards the North Pole, would the golf ball actually make it there? And the answer, turns out, is not really yes. It's going to be no. So what's happening when you hit the golf ball, before you hit it and it's just on the ground at the equator, you don't know this because everything has the same radial velocity, but you, the golf ball, the golf course, everything is moving west to east at the radial speed or the radial velocity of the equator. Now, as soon as you hit that golf ball and it detaches from the Earth's surface, it'll begin to head north, but it has no idea that the radial velocity of the Earth beneath it is slowing. So what happens is the radial velocity of the golf ball ends up remaining the radial velocity of the equator, which becomes faster than the radial velocity beneath it as it heads towards the north. So basically, the Earth beneath the golf ball is slowing down. As a result, the golf ball appears to veer off to the right of its initial motion, which was straight south to north. Now, you can do the same thing at the North Pole. You can actually take a flight to the North Pole, put your golf ball, now orange probably, on the snow and ice, and then hit it as hard as you can towards the equator. Now, when the golf ball starts at the North Pole, it has a radial velocity of 0. But as it heads towards the equator, the radial velocity of the Earth beneath the golf ball will begin to speed up, while the golf ball has a 0 radial velocity. And so the Earth will begin to spin west to east about its axis, and the golf ball will again appear to veer off to the right of its initial motion. Now, to figure out what is the left and the right of the motion, you have to basically put yourself at the end of the arrow of motion and then hold your hands out. So if you start with this red arrow and you hold your hands out as you're looking towards the north, right will be over here, left will be over here. If you take the arrow and you direct it towards the equator, right will be over here and left will be over here. So no matter what happens in the northern hemisphere, when you actually have motion over very large distances, the changing of the radial velocity of the Earth beneath those objects will always cause the objects to appear to veer off to the right of their initial motion. And that leads us to our definition of the Coriolis force. First of all, the Coriolis is an apparent force. We call it an apparent force versus a real force because nothing is really pushing the object, the air, the golf ball, whatever it is that's moving. Nothing's forcing it to the right. The objects appear to veer off to the right simply because the radial velocity of the planet beneath the moving object is changing. So the Coriolis force is an apparent force, and it always acts 90 degrees to the right of the motion in the northern hemisphere. Always 90 degrees to the right of the motion. Now, let me give you a couple of more details about the Coriolis force. Again, it's apparent, so it's an apparent deflection, and it's of large-scale motions. I'll note when we get to severe weather in Investigation 11B that the Coriolis force actually is not what leads to the rotation or the spin that we see with tornadoes, because the motion is too slow. The Coriolis force only acts upon motions that take place over large distances. And again, it's caused by the latitudinal dependence of the Earth's radial velocity. I give you a little bit of trigonometry here, and you don't need to worry about these numbers, but just to give you an idea of what the radial velocities are at different latitudes. At the equator, the west to east velocity of the planet is actually 1,036 miles per hour. So if you are at the equator and you're just standing at the equator, you, the land, the palm trees, everything is moving from west to east at 1,036 miles per hour. And of course, you don't have any notion of that happening because everything is moving at that speed. Now, if you're in good old Bowling Green at 41 degrees, 41.37 degrees, we begin to slow down. And so the radial velocity slows down from 1,036 miles per hour at the equator to a still pretty speedy 777.8 miles per hour in Bowling Green. Now, again, as you continue to move north towards the North Pole, the radial velocity will slow and slow until you get to the North Pole, and the radial velocity is just 0. And again, it's the motion over our spherical Earth as radial velocity changes, basically decreases from equator to a pole, that leads to our apparent Coriolis force. More details. Not only does the Coriolis force act 90 degrees to the right in the northern hemisphere, it acts 90 degrees to the left of the wind or motion in the southern hemisphere. the magnitude of the Coriolis force will increase as the wind speed increases, and it will equal 0 when the wind is calm. In better words, you cannot deflect motion when there is no motion. And so when the winds are still or calm, there's no deflection, there's no Coriolis force. And then as the wind speed picks up and the motion becomes faster, then the magnitude of the deflection will become larger as well. So the magnitude of the Coriolis force increases with the wind speed. And then for a given wind speed, the Coriolis force will be 0 at the equator, and its magnitude will increase with latitude. We're not really going to look at this third one at all in our class. I'm just putting it down there for completeness. So how does the air respond when just the pressure gradient and Coriolis force act upon it? Now you can basically come up with winds at the surface or at upper levels just looking at these two forces. In the investigations manual, they actually give you isobar values that are in the 600s to indicate that it's upper level. I actually changed those values to the same values that we see throughout the investigation. So 1008 to the south and 1000 to the north. Just indicating to you that this is what we would see at the surface if there were not friction, and this is what we pretty much see at upper levels because there isn't friction. And I'll tell you in a little bit why it is that I'm actually looking at this with surface isobaric values rather than upper level values, although we could use both. Okay, so basically the pressure gradient force arrow, or I'm going to call it a vector. I'm sure we're going to fall into the terminology of using the word vector, but vector just means arrow. So the pressure gradient force vector is red, the Coriolis force vector is going to be blue, and the winds throughout are going to be indicated by this green dash curve. Okay, so how does the air respond when the pressure gradient and the Coriolis force act upon it? Well, first of all, we're going to start with wind at this black dot that is calm. Therefore, the only force that can act upon it is the pressure gradient force, and there is a pressure gradient because we do have pressure varying over distance. And the pressure gradient force is going to act from high in the south to low in the north pressure, and it is going to be directed perpendicular to the isobars. So the pressure gradient force is going to kick things off. So it initiates the wind, which again is going to be green. Now, once the wind begins to blow, the Coriolis force will immediately come into play and it'll act 90 degrees to the right of the wind. So if you take a look at point B, and our wind is basically directed with these green dashed lines, you can see our wind is basically southwest to northeast here, and our Coriolis force vector or arrow is directed 90 degrees to the right. So the Coriolis force throughout, as long as we have a wind, the Coriolis force will always act 90 degrees to the right of that wind. And in our class, I'm just going to keep us in the northern hemisphere. We don't live in the southern hemisphere, so I'm going to keep us just in the northern hemisphere. Now, what you'll see at point B, C, and even D is that the pressure gradient force vector is bigger than the Coriolis force vector. In better words, the magnitude of the pressure gradient force is larger than that of the Coriolis force. Now, what ultimately happens with our forces is that what they try to do is they try to come into some sort of a balance so that the wind will result from a balance between these forces. When we only have two forces, in this case, the pressure gradient and the Coriolis force, the balance will occur when the magnitude of the forces is equal and the forces are directed in opposite directions. And so what you see as we move along from B to C to D to E is that the magnitude of the Coriolis force vector is getting larger and larger. So as we go from A to B to C to D, the wind is actually accelerating. The wind is accelerating, the Coriolis force magnitude is increasing, and what you'll see is that the arrow is getting longer, and eventually it is moving to a point where we have a perfect balance between the two forces, where the pressure gradient force is directed towards the north, the Coriolis force is directed towards the south, and it's 90 degrees to the right of the wind. Now I want to note here that the magnitude and direction of the pressure gradient force vector is not in any way influenced by the wind. The pressure gradient force vector simply is a measure of the rate at which pressure is changing over distance, and because the rate is uniform and it's always south to north, the pressure gradient force magnitude doesn't change and its direction doesn't change. So it's a Coriolis force that adjusts, and it keeps adjusting until we achieve this balance. And so the wind accelerates and it turns to the right to strike a balance between the pressure gradient and Coriolis forces, which is what we achieve here at point E. Once this balance is achieved, we're basically where we need to be. And there'll be no more adjustments in the forces or in the wind. And the wind that we get when the forces are in balance represents the balance between these forces. So the acceleration and turning will continue until balance between the pressure gradient and Coriolis forces is achieved. So let's just put this figure back down again. And I'm going to define the geostrophic wind. It's this V sub G right here. The geostrophic wind is the wind that results from a balance between the pressure gradient and Coriolis forces. It's always parallel to the isobars. It always blows parallel to the isobars. Low pressure will always be to the left of the geostrophic wind, and high pressure will always be to the right of that geostrophic wind arrow. Again, to figure out where left and right are relative to the arrow or vector, you need to basically put yourself at the end or the tail of the vector and look down the arrow to the arrowhead, and then just put your arms out left and right. So you'll see again that low pressure is on the left side of our arrow and high pressure is on the right side of our arrow. Now, the reason we take a look at the geostrophic wind at the surface, even though we're going to see that winds at the surface aren't geostrophic, is because the geostrophic wind basically explains about 80 to 85% of observed winds at the surface. Now, when we go above the surface and we look at upper air maps and winds at upper levels, friction goes away. And so what we'll see at upper levels is that the winds actually are largely geostrophic. We'll see at upper levels that the winds typically are parallel to the isobars or isoheight lines. And we're going to talk about isobars and isoheights fairly soon. So we look at geostrophic winds at the surface. It's still useful, even though the book doesn't really talk about geostrophic winds at the surface, because in reality, winds are not geostrophic at the surface, but they're close. Now, let's talk about the impact of friction on the geostrophic wind at the surface. So imagine we start with geostrophic winds at the surface. So here's low pressure to the south, or high pressure to the south, low pressure to the north, just like we've seen so far. And what I'm going to begin with are my vectors, basically the geostrophic wind representing a balance between the pressure gradient force and the Coriolis force at the surface. Ignore everything to the right of this right now. Now, when you add friction, so when you actually consider the existence of friction at the surface, friction always acts opposite the wind. It always acts opposite the motion. And you probably know that all you need to do is, while you're watching, just rub your hands together, and you'll feel that warmth that's generated by rubbing your hands together. That's caused by the friction between your palms. And the friction is always acting opposite the motion. So friction always will act opposite the wind. And so when you get friction, the first thing that will happen is it will cause the winds to decrease. Now, the geostrophic wind is a very special wind. It represents a balance between the pressure gradient and Coriolis forces. So as soon as we add friction, the geostrophic wind is going to become just a plain old wind. And now what I want you to do is to come over here to number 2, and we'll see what happens when we add friction to all of this. The first thing that's going to happen is the wind is going to decrease, and that's right here. So what I'm doing is I'm taking a little slice off of our initial geostrophic wind. The second thing that happens is that because the wind speed decreases, the magnitude of the Coriolis force is going to decrease. So I'm going to take a little slice right off of the Coriolis force. So I'm taking some slices off of first the wind and then the Coriolis force because friction causes the wind to slow down. Now, the third thing that results from this is that the pressure gradient force will become the dominant force. So the pressure gradient force, again, is not impacted by any of these other forces. It just measures the rate at which pressure is changing over distance. So the pressure gradient force becomes the dominant force. As a result of that, the wind is going to be pulled towards the pressure gradient force, or the wind is going to turn towards the pressure gradient force. And so you see this dashed arrow or vector, which represents our new wind, which is being pulled towards the pressure gradient force. Then our Coriolis force is going to turn with the wind to maintain its 90-degree angle with the wind, and our friction is going to turn with the wind so that friction continues to act opposite the wind. The result is going to be what we actually do observe at the surface. And our wind now, what you're going to see, is that the wind actually crosses the isobars at an angle from high to low pressure. And this is what we observe at the surface. Now, the degree to which the wind crosses the isobars at an angle from high to low pressure depends on a lot of different details, not least of which is the magnitude of friction. So friction is actually pretty small over ice and bodies of water where things are relatively smooth, whereas you can imagine in mountain ranges and heavily forested areas, friction is much larger. So there's no perfect angle. There's no set angle at which the wind crosses the isobars. Also, what you tend to see is that the wind crosses the isobars at a larger angle when the wind is lighter and at a smaller angle when the wind speeds are stronger. So there's just a lot of detail that we don't really worry about in our class. As long as you've got this last check mark, that the wind crosses the isobars at an angle from high to low pressure, you're going to be good. Okay, now I'm going to give you some examples here that are not given in the investigation that I hope will actually help you along, not just with investigation 8A, but with investigation 8B, because you're going to need to know how to do this, certainly in 8A and in 8B. So what I'm going to do is I'm going to start with an example of a surface map from the 11th of October 2022, so this is not in your investigation, and then I'm going to show you how to actually take a station model and draw the vectors that act on the air at that particular location. And I believe we're going to choose a point around low pressure. Our low, by the way, is centered up here in Canada. We're going to choose a location in North Dakota. So let me just put a box around it right there. And then what we're going to do is we're going to zoom in on the northern plains so that we can see a little bit better how this works. So here's our map, and here's our station in North Dakota. Now what I'm going to do is I'm going to first draw a couple of different vectors and see how it all works and how it all comes together. And I'm going to begin with the pressure gradient force, because the pressure gradient force is always directed from high to low, perpendicular to the isobars. Now lower pressure is up here to the northeast of the station, but you use the local isobars to figure out the direction of the pressure gradient force vector or arrow. And here's high pressure here. So pressure gradient force is going to be directed straight west to east. It's perpendicular to these isobars. Now the next vector that I'm going to draw is going to be the wind vector. Now to get the wind vector right, the wind vector is going to cross the isobars at an angle from high to low pressure, with lower pressure on its left, higher pressure on its right. So here is the wind. And what you'll see are the lower pressures are here to the northeast on its left, the higher pressures are to the southwest on its right. So here is our wind arrow or vector. Now, once you get the wind arrow or vector, then what you do in terms of getting the Coriolis force is you have to again put yourself at the end of this wind vector and then look towards the arrowhead and figure out which is left and which is right. In this case, right is to the southwest. So here is our Coriolis force vector, and then here is friction opposing the wind. Now I'm going to take friction out for a second because I also want to point out that wind is quite easy in the sense that if you take a look at the wind direction line going into our station model, remember to get the wind direction, you put yourself at the end of the line and then you look straight in towards the station model. So this is a northwest wind. The wind is blowing from northwest to southeast. So in order to get the wind vector, the direction that the wind is pointing towards, you just basically continue this arrow directed northwest to southeast. So here again is friction. So meteorologists will refer to this as a vector diagram. So all four arrows start at the same location, our station, and they extend out from the station so you can see how the wind is being impacted by the forces that act on the air at this location. Pressure gradient force, Coriolis force, friction. So this is an example of the wind being directed in towards lower pressure, crossing the isobars at an angle from high to low pressure. All right, here is our next example, and this is the same day. I'm going to choose an example in Georgia. Now I'm going to actually cheat on the winds a little bit because these winds are not really representative of what you would typically see in an example where you have a vector diagram with pressure gradient, Coriolis, and friction. So I'm going to, again, hover in here a little bit more closely, start with our pressure gradient force, high to low pressure, perpendicular to the isobars. Here's our pressure gradient force. Now, if I were drawing the wind vectors so that it's actually what's being reported here, what you would see is that the wind would actually be pretty much parallel to the isobars. But I'm going to draw the wind vector so that it's actually directed out from the high at an angle from higher to lower pressure like this. And then I'm going to have the Coriolis force directed 90 degrees to the right of the wind. and then our friction opposing the wind directly like this. So here's our vector diagram for a station in Georgia, basically extending out from an area of surface high pressure. And you can see the wind in this case is directed at an angle across the isobars from high to low pressure. So you're going to be asked to do this in investigation 8B as well. And so I'm giving you a little bit of a taste of what it is you're going to be expected to do. So I want you to watch this video a couple of times if you are having any issues with drawing these vectors, these arrows. And by all means, don't hesitate to ask me questions if you have any problems with this, because this is kind of a new concept and it may be a bit challenging for some of you. It's very spatial in nature. Some of you are going to do really well with this. Some of you are going to find it really, really challenging. So that's pretty much everything I want to say about investigation 8A. If you have any questions whatsoever about the investigation or anything that I've said here, because I've added quite a bit to the investigation, by all means, post a question to the discussion board, or feel free to ask me live during my office hours on Zoom, Wednesday evening, 7:30 to 8:30 during the fall, and Sunday afternoons from 2 to 3. But that's it, that's all. I'm going to end the video now, post it on YouTube, and you'll see an announcement when it's ready for you to watch.